650 light-years away, something has been living inside a star. Not near it, not beside it. Inside its outer atmosphere, ploughing through gas hot enough to strip the paint off a spacecraft, orbiting once every 110 days, as if that were an ordinary way to exist. What could survive there? What was Hubble actually looking at when it caught the wake this object leaves behind? And why did 3 separate teams, using 3 separate telescopes, spend the better part of a decade insisting it wasn't real before admitting it was? This is the story of a star the length of human civilization has watched every clear night for thousands of years. A star bright enough to name, mythologize, and worship, and we still manage to miss the thing living inside it. Look up on a cold, clear winter evening, somewhere north of the equator, and you will find it without trying. Orion the Hunter rises in the east, 3 stars strung in a tight diagonal line for his belt, and above his left shoulder, his right, if you imagine him facing you, burns a single point of orange-red light that refuses to sit still in the way the other stars do. It flickers with an edge that feels almost deliberate, a slow-motion pulse, rather than the simple twinkle of atmospheric distortion. That light is Betelgeuse, and it has been watched, worshipped, measured, and mythologized by nearly every human culture that ever looked up with curiosity instead of fear. The name itself carries a small joke buried inside a translation error 9 centuries old. Medieval European scholars, working from Arabic star catalogues, rendered Yad al-Jawzar, the hand of al-Jawzar, the name Arab astronomers gave to the constellation figure we now call Orion, into something that sounds to modern ears unmistakably vulgar: Betelgeuse. The mistranslation stuck. It has stuck for so long that even professional astronomers, when they say the name aloud at conferences, sometimes pause for half a second, aware of the accidental comedy embedded in one of the most studied stars in the night sky. I find a strange comfort in that. Even our most rigorous science carries fossils of human error, translated and mistranslated across centuries, refusing to be scrubbed clean, but strip away the etymology, and what remains is something almost impossible to hold in the mind at full scale. Betelgeuse is a red supergiant, one of the largest stars visible to the naked human eye anywhere in Earth's sky, with a radius somewhere in the neighbourhood of 700 times that of our own Sun. NASA's own estimate puts it even more starkly. More than 400 million suns could be packed inside Betelgeuse's volume, side by side, and there would still be room to spare. If you swapped Betelgeuse into the centre of our own solar system, replacing the Sun outright, its surface would swallow Mercury, Venus, Earth, Mars, and would very likely extend out somewhere close to the orbit of Jupiter. Every planet we have ever sent a robot to would be sitting inside the star's own outer atmosphere, not orbiting a sun but drowning in one, and yet Betelgeuse is, by stellar standards, an infant. Current estimates place its age at somewhere around 10 million years, a number so small in astronomical terms that it barely registers, given that our own Sun has been quietly burning hydrogen for roughly 6 billion years and has by most estimates another 5 billion left to go. Betelgeuse will not get anywhere close to that kind of longevity. Stars of enormous mass burn through their nuclear fuel at a ferocious, almost reckless pace, and Betelgeuse, with a mass somewhere between 16 and 19 times that of our Sun, has already exhausted the hydrogen in its core and moved on to burning heavier elements in a rapid, unstable sequence that will end, almost certainly, in a supernova. 10 million years old and already dying. That contradiction alone should tell you something about how differently stars can be built to live. Humans have been tracking this star's strange behaviour for far longer than we have understood any of the physics behind it. Ancient Chinese astronomical records from roughly 2,000 years ago describe a star in that region of the sky with a colour closer to yellow than red, a detail confirmed remarkably by careful reanalysis of historical texts published in the past several years, which found that Ptolemy himself, writing in the 2nd century, called Betelgeuse a bright, reddish star, suggesting the star's surface temperature and colour have shifted meaningfully within recorded human history. A star does not typically change colour on a timescale, a civilization can witness within its own written records. Betelgeuse did. That alone should have been the first clue that something unusual was happening to this star, decades before anyone had the instruments to look closely enough to ask why. The formal scientific record of Betelgeuse's strangeness begins in 1836, when the British astronomer and polymath Sir John Herschel, son of William Herschel, discoverer of Uranus, turned his attention to the star and documented, in careful, unhurried 19th century prose, that its brightness rose and fell over time in a way that seemed neither random nor perfectly regular. Herschel noted that on some nights the star rivaled Rigel, Orion's other brilliant anchor star, in brightness, and on other nights it dimmed noticeably below it. He had, without fully realizing what he was documenting, become the first person in the historical record to formally observe stellar variability in Betelgeuse. It would take astronomers another 150 years, and technology Herschel could not have imagined, to even begin to understand what he was seeing. By the 20th century, astronomers had confirmed that Betelgeuse pulsates on a primary cycle of roughly 400 days, the star physically swelling and contracting, its surface temperature and luminosity rising and falling together in a rhythm that, once identified, made a certain intuitive sense. Massive, unstable stars near the end of their lives often pulsate this way, their outer layers heaving in and out like a chest struggling to breathe. That part of the puzzle eventually got solved, but buried underneath that 400-day heartbeat was a second, slower, much stranger rhythm, a variation stretched out over roughly 6 years, a period long enough that no single astronomer's career in the pre-computer age could easily capture more than a handful of cycles. This longer pulse resisted every explanation offered for it, and it would go on resisting for more than a century. That second rhythm is where our story actually begins. Because a star that simply breathes in a single, understood pattern is a solved problem, filed away in a textbook, unremarkable to anyone but a specialist. A star that breathes twice on 2 different clocks, one of which nobody could explain, that is a live wire. That is the kind of anomaly that keeps astronomers awake, that gets whispered about at conferences for generations, that eventually attracts exactly the kind of obsessive, decades-long attention that turns a curious footnote into one of the most significant stellar discoveries of the 21st century. Herschel saw the flicker in 1836. It would take until the 2020s for anyone to understand what or who was truly causing it. By the early 20th century, astronomers had a name for what they were seeing in Betelgeuse's slower 6-year rhythm, the long secondary period. It is, admittedly, an unglamorous name for a genuinely stubborn mystery, the kind of clinical, hedge-your-bets label scientists reach for when they have observed a pattern clearly enough to measure it, but have no confident story yet for why it exists. And Betelgeuse was not even the only star showing this behaviour. Astronomers studying other red giants and supergiants across the galaxy had noticed similar long, slow variations layered on top of the star's primary pulsation cycles, variations that stubbornly refused to fit the standard models of how a pulsating star should behave. Something was happening across an entire class of aging, swollen stars, and nobody could say with confidence what it was. The candidate explanations, when they eventually arrived, were not short of imagination. One school of thought proposed enormous convective cells, turbulent, boiling patches on the star's surface, some of them potentially large enough to span a significant fraction of the entire stellar disk, rising and cooling and sinking again over multi-year timescales, dragging the star's overall brightness up and down as they did. This was not a wild guess. Hubble had already given astronomers direct visual evidence that Betelgeuse's surface is mottled, blistered, and turbulent in a way no star closer to us, including our own comparatively placid Sun, had ever been photographed to be. A second camp pointed to dust, enormous clouds of grain periodically ejected from the star's surface, drifting through the line of sight between Betelgeuse and Earth, dimming its apparent brightness the way smoke dims a street lamp. A third camp invoked magnetic activity, borrowing loosely from what we know of sunspot cycles, suggesting some analogous, though far more violent, magnetic process might be inflating and deflating the star's outer layers on a multi-year clock. And running quietly underneath all three of these, refusing to go away no matter how many times it was dismissed, sat a fourth idea that Betelgeuse was not alone, that somewhere close, perhaps uncomfortably close, a second, much smaller star was orbiting it, and that the 6-year rhythm scientists kept measuring was not something Betelgeuse was doing to itself at all. It was something being done to it. The companion star hypothesis is, in astronomical terms, almost embarrassingly old. Proposals of a hidden partner star orbiting Betelgeuse stretch back to at least the 1990s, appearing and disappearing in the scientific literature the way a persistent rumour circulates through a small town, never quite confirmed, never quite killed. Every few years someone would run the numbers again, note that a companion explained the 6-year cycle more elegantly than convection or dust ever managed to, and propose another search. Every few years the search would come back empty, and the idea would recede again into the background hum of unresolved astrophysics. There is something almost unbearably human about that pattern. A century of astronomers, generation after generation, independently arriving at the same suspicion, checking, failing, and passing the question down to whoever came next. Then came 2019, and the star did something that terrified an entire planet's worth of amateur astronomers and more than a few professional ones. Beginning in October of that year and stretching into early 2020, Betelgeuse's brightness dropped with a speed and severity nobody alive had ever observed from it. At its dimmest in February 2020, the star had faded to roughly a third of its normal brightness, a decline so visible that you could genuinely watch it happen from your own backyard, night after night, without a telescope, just with the naked eye and a memory of how bright the star used to be. Social media exploded with speculation. Amateur astronomy forums filled with breathless threads asking the same question in a dozen different phrasings. Was this it? Was Betelgeuse, a star already known to be near the violent end of its life, already flagged as one of the nearest supernova candidates to Earth, finally about to explode, the event picked up a nickname almost instantly: the Great Dimming. I will admit that I find something genuinely moving about how much cultural energy that dimming absorbed in such a short window. For a few months, a red supergiant 650 light-years away became a kind of shared global anxiety, discussed on morning television and late-night comedy shows alike, treated as a countdown clock to a cosmic event that would, if it truly happened, be visible in Earth's daytime sky for the better part of a year. It was, in its own strange way, one of the more honest moments of public engagement with astronomy in recent memory. Millions of people, most of whom had never before wondered about a star's internal chemistry, suddenly desperate to understand exactly how close the end of Betelgeuse's life might actually be. The end, as it turned out, was not near, at least not on any timescale relevant to a human news cycle. Astronomers using the Hubble Space Telescope, led in large part by Andrea Dupree at the Centre for Astrophysics, pieced together what had actually happened, and the explanation, once assembled, was almost more strange than an outright supernova would have been. Betelgeuse had not dimmed because it was dying. It had dimmed because it had, in the words later used to describe the event, essentially sneezed, violently ejecting an enormous amount of hot plasma from its surface into space, material that cooled rapidly as it expanded outward and condensed into a dense cloud of dust. That dust cloud then drifted directly across our line of sight to the star, blocking a significant portion of Betelgeuse's light from reaching Earth at all. The star itself had not grown fainter in any fundamental sense. We were simply looking at it through smoke. That explanation resolved the immediate panic. It did not resolve the deeper mystery. Because the Great Dimming, dramatic as it was a one-time traumatic event, a surface mass ejection, a stellar hiccup on a scale never directly observed before in any star. The long secondary period, the strange 6-year, 2,100-day rhythm that had puzzled astronomers since before any of them were born, was still there, still ticking along underneath everything, entirely unexplained by dust clouds or one-off eruptions. If anything, the intense global attention triggered by the dimming did something the mystery itself had failed to do for 100 years. It pulled fresh eyes, fresh funding, and fresh telescope time toward Betelgeuse, all at once, from teams who might otherwise never have prioritized re-examining a century-old open question. And so, in the years immediately following the Great Dimming, a strange kind of scientific momentum built around Betelgeuse that had never existed before. Teams that had spent their careers on other stars entirely began pulling archival Betelgeuse data out of storage, running it through statistical methods that simply did not exist when the long secondary period was first documented. If a hidden companion really was out there, tucked into an orbit so close to Betelgeuse's surface that it was functionally invisible against the supergiant's overwhelming glare, this was the moment, for the first time in a century of trying, that astronomers finally had the tools, the motivation, and the decades of accumulated data needed to actually go looking properly. The question that had outlived every astronomer who first asked it was finally about to get an answer. But first, it was about to get considerably harder to solve. Here is the problem with hunting for a companion star hiding in the glow of Betelgeuse, and it is worth sitting with the scale of it for a moment before moving on, because the difficulty is not incidental to this story, it is the story. Betelgeuse, at its peak, shines with a luminosity somewhere in the range of 90,000 to 150,000 times that of our Sun. A hypothetical companion star small enough and dim enough to have evaded detection for over a century, orbiting close enough to explain a 6-year brightness cycle, would necessarily be a small, cool, comparatively faint object, plausibly only a few times the mass of our own Sun, and shining with only a tiny fraction of Betelgeuse's overwhelming output. Trying to directly image such an object sitting immediately adjacent to Betelgeuse is, in the words more than one astronomer has used almost verbatim across different papers and interviews, roughly equivalent to trying to spot a lit match held directly in front of a floodlight, from 650 light-years away, through the smeared, turbulent optical distortion of Earth's own atmosphere. Floodlight does not merely outshine the match, it obliterates any trace that the match exists at all, scattering enough stray light across the detector to erase a target that faint before it can even register. This is why, for years, even the best available evidence pointing toward a companion remained frustratingly indirect. Between 2019 and 2024, several research groups, working independently with different instruments and different statistical approaches, began circling back to old data with new eyes, and their conclusions started to converge in a way that felt less like coincidence and more like triangulation on something real. One of the most significant efforts came from a team associated with the Centre for Astrophysics' Institute for Theory and Computation, including Morgan McLeod, Andrea Dupree, Caroline Huang and Avi Loeb, who in 2023 and 2024 pulled together roughly 127 years of observational data on Betelgeuse's brightness and radial velocity, its motion toward and away from Earth, measured through the subtle shifting of its spectral lines. 127 years. Think about what that number actually represents. Multiple full human lifetimes of astronomers, most of them long dead, each recording a sliver of data they had no way of knowing would eventually be stitched together into evidence for something none of them lived to see confirmed. When McLeod's team modelled that century plus of data, the numbers pointed clearly in one direction. A companion star, orbiting Betelgeuse on a period matching almost exactly the observed Tuti 100-day long secondary period, explained the data with a precision that no combination of convection, dust, or magnetic activity had ever managed. The predicted orbit was staggeringly tight, an average separation of roughly 4 astronomical units, meaning the companion, if it existed, would spend a significant fraction of every orbit not merely near Betelgeuse, but physically inside the star's own extended outer atmosphere, dragging through gas that Betelgeuse itself had puffed outward over millennia of slow, steady mass loss. The predicted orbital velocity came out to roughly 43 kilometers per second, fast enough that, if you could somehow stand on this companion and look outward, the sky itself would blur with the speed of your own motion through another star's exhaled breath. The team went further, and this is where the story sharpens into something with real stakes attached. Using the predicted orbital geometry, they calculated the specific dates on which the hypothetical companion would swing to its point of maximum apparent separation from Betelgeuse as seen from Earth. The moment in its orbit when it would be easiest, if not yet easy, to spot directly against the glare. Two independent papers published in 2024 converged on the same prediction. December of that year would offer the best observing window in years, a brief geometric alignment when the companion, if real, would swing far enough from Betelgeuse's blinding disk that a sufficiently sensitive instrument might catch it standing alone against the dark. This was, in a very real sense, science placing a bet with a fixed expiration date, predict where an invisible object should be, name the exact months when it should be visible, then wait and find out, in public, whether you were right, or whether a century of speculation was about to collapse into another dead end. Before that window even arrived, however, one earlier attempt had already tried, and, on the surface, failed. Astronomers had previously pointed both the Hubble Space Telescope and the Chandra X-ray Observatory directly at Betelgeuse, searching specifically for a companion, using two of the most capable observatories humanity has ever put into orbit. Neither instrument found anything conclusive, no detection, no confirmation, just silence and the uncomfortable possibility that either the companion did not exist at all, or that it existed in a form so faint, so deeply buried in Betelgeuse's atmosphere that even our best space telescopes simply could not separate its light from the supergiant's overwhelming glow. I find that failure, honestly, more compelling than a clean success would have been, because it meant that even after the theoretical case had been built, even after a century of accumulated brightness data had been mathematically distilled into a specific, falsifiable prediction, nature still had the final word on whether our instruments were good enough to see it. Hubble is, without exaggeration, one of the most sensitive optical telescopes ever constructed, a machine that has photographed galaxies so distant their light left them before Earth itself finished forming. And Hubble looked, and Hubble came back with nothing usable. That is not a small failure. That is a direct demonstration of just how extreme the contrast problem actually is. A floodlight so overwhelming that even a spacecraft capable of resolving individual stars in neighbouring galaxies could not resolve a single faint companion sitting practically on top of the brightest, closest supergiant in our sky. So the astronomical community found itself heading into late 2024 in an unusually tense and specific position. A century-old mystery, a mathematically rigorous prediction built on 127 years of painstaking human observation, pointing to an exact orbital geometry and an exact window of visibility. Multiple previous searches using genuinely world-class instruments coming back empty, and a hard deadline, December 2024, after which the companion, if it existed at all, would swing back behind Betelgeuse's glare and disappear from view for years, not to offer another clean observing opportunity until 2027. Astronomers had, in other words, one shot on a fixed astronomical clock that no amount of funding or persistence could accelerate. If nobody managed to catch it in that window, the question that had outlived Herschel, outlived a century of failed searches, and outlived every scientist who had ever proposed the companion hypothesis, would simply have to wait again, possibly for years, possibly for a generation, possibly forever, if the technology available in 2027 turned out to be no better suited to the task than it had been in 2024. Somewhere in Hawaii, at an observatory perched more than 4,200 meters above sea level on the dormant volcano Mauna Kea, a team led by Steve Howell at NASA's Ames Research Center was already preparing an instrument built for exactly this kind of impossible contrast problem. It had a name that sounded almost too whimsical for the stakes involved: Alapeek, Hawaiian for fox. And it was about to attempt something that Hubble itself, pointed at the same target with far greater fame and far greater cost, had already failed to do. There is a particular kind of tension that builds in astronomy in the days before a predicted observing window opens. Not the tension of a launch countdown, with its rockets and its roaring engines and its televised anxiety, but something quieter and, in its own way, more nerve-wracking. It is the tension of knowing exactly when nature has agreed, however briefly, to show its hand, and knowing that if your instrument is not sensitive enough, if the atmosphere is not cooperative enough, if the data reduction is not clever enough, you do not get to ask nature to repeat itself on your schedule. You wait for the next appointment, years away, and hope someone else's technology has caught up by then. Steve Howell's team pointed the Gemini North Telescope at Betelgeuse using a speckle imaging technique, a method that works by capturing an extremely rapid sequence of very short exposures, each one frozen fast enough to outrun the blurring, shimmering distortion that Earth's turbulent atmosphere normally smears across every ground-based astronomical image. Combined with Gemini North's 8.1-metre primary mirror, one of the largest single optical surfaces on any telescope on the planet, Alapeek was able to achieve a resolution sharp enough to attempt something that had defeated Hubble itself, separating a faint point of light from the star it was hiding beside. And it worked in the data. Right where the century of accumulated calculations said it should be, sat a compact source of light, faint, 6 magnitudes fainter than Betelgeuse itself in visible wavelengths, which translates to roughly 250 times dimmer, a difference so extreme that describing it in ordinary brightness terms barely conveys how close to invisible this object actually was. But present in exactly the position the orbital models had predicted for December 2024, the exact month 2 independent teams had circled on a calendar months in advance. Howell's team estimated the companion's mass at roughly 1, 5 times that of our Sun, and characterized it as an A or B-type pre-main sequence star, a young, hot, blue-white object still in the process of gravitationally collapsing toward the point where hydrogen fusion would finally ignite in its core, not yet a fully grown star in the technical sense, still forming even as its ancient, dying neighbour burned through its final stable years. The companion, they found, orbits at an average distance of roughly 4 astronomical units from Betelgeuse's centre, a distance so close that it places the companion not merely near the supergiant, but physically inside Betelgeuse's own vast, extended outer atmosphere, wrapped in gas the giant star had already exhaled outward across its own lifetime. Papers that predicted Betelgeuse's companion believed that no one would likely ever be able to image it, Howell said afterward, and there is a particular satisfaction embedded in that sentence that is worth pausing on. Even the scientists who had done the math, who had built the models and calculated the predicted position with genuine mathematical confidence, had assumed the actual image itself was functionally out of reach, that the contrast problem was simply too extreme for any real telescope to overcome. Alapeek did what no other instrument had managed. It looked directly at one of the most extreme brightness contrasts in the observable night sky and returned a picture anyway. But, and this is the part of the story that responsible science almost always insists on, however unglamorous it makes for headlines, the detection was not clean, not remotely. The signal-to-noise ratio in the data, a statistical measure of how confidently a real signal can be distinguished from random instrumental noise, came out to roughly 1.6. In the world of professional astronomy, a signal-to-noise ratio that low sits in genuinely uncomfortable territory. Astronomers typically want values many times higher before they are willing to call something a confirmed detection rather than a tantalizing hint. René Oudemajer, an astronomer at the University of Leeds who was not part of the discovery team, put the skepticism plainly when asked about the result. It is certainly intriguing to consider the possibility that a companion is detected, but the fact of the matter is that the signal-to-noise of this effect is quoted to be 1.6. Such values are widely regarded as non-detections. By the team's own honest accounting, there remained roughly a 10% chance that what they had photographed was not a companion star at all, that it was instead an artifact, a fluke, a trick of noise dressed up to look exactly like the thing everyone had spent a century hoping to find. Orbital motion, the single most convincing piece of evidence that an object is genuinely gravitationally bound to a star, rather than a coincidental point of light or a processing artifact, had not yet been observed at all. I will be honest about how I feel reading that caveat, because it matters to the shape of this entire story. I find something almost more compelling in that uncertainty than I would in a clean, unambiguous confirmation, because this is what real discovery actually looks like, most of the time. Not a single triumphant unveiling, but a stack of partial evidence, each piece imperfect on its own, gradually accumulating weight until the alternative explanations start to feel less plausible than the discovery itself. Betelgeuse's companion did not arrive with a press conference and a champagne toast. It arrived with a 90% confidence level and an honest admission from the discovery team that they might be wrong. So the story does not end there, with a shaky image and a 10% margin of doubt hanging over one of the most consequential stellar discoveries in decades. It continues 18 months later on the other side of the planet with an entirely different telescope, an entirely different technique, and an entirely different team who had no interest in confirming Howell's specific detection. Only in independently answering the same underlying question with their own instrument, their own methods, their own reputation on the line, a French-led team headed by Miguel Montargis at the Observatoire de Paris had, since 2021, already built a reputation studying Betelgeuse closely. It was Montargis himself who had led the earlier investigation, confirming that the Great Dimming had been caused by a dust cloud rather than an imminent supernova. Now, using the SPHERE instrument mounted on the European Southern Observatory's very large telescope in Chile's Atacama Desert, an instrument originally engineered to hunt for faint exoplanets around distant stars, not stellar companions around supergiants. Montargis' team pointed their optics at Betelgeuse in December 2024, the exact same predicted window Howell's team had already exploited from Hawaii, and began the long, painstaking process of processing the resulting data. What they found, once the processing was complete, left even the lead scientist visibly shaken by his own result. I jumped from my chair when I saw the processed images, Montargis recalled afterward. There, in the SPHERE data, sat a bright, unmistakable point of light exactly where the orbital predictions said a companion should be, and it was not faint in the ambiguous, statistically fragile way Howell's Gemini detection had been. This image was, by the team's own description, the clearest direct picture ever obtained of the object now provisionally named Betelgeuse b. We have shown that Betelgeuse is not single, it is accompanied by a faint stellar companion, Montargis stated, calling the finding the conclusion of a century-long quest. The two independent detections agreed on the essential shape of the discovery, a companion orbiting deep inside Betelgeuse's extended atmosphere, roughly where a century of statistical modelling said it should be. But they disagreed notably on the object's mass, where Howell's team had estimated roughly 1.5 solar masses. Montargis' more sensitive VLT data suggested something heavier still, somewhere between 2 and 3 times the mass of our own Sun. Because it is more massive than predicted, we see it, Montargis explained, almost apologetically, as if the universe had been slightly more generous than anyone's models had assumed, and that generosity was the only reason the companion had finally become visible to sufficiently sharp eyes. The fact that we can still discover a nearby companion, more massive and brighter than the Sun, around such a well-studied star is remarkable, he added. These are among the best moments in science, seeing something new, unexpected. Even here, though, the team stopped short of declaring absolute victory. confirming true orbital motion, watching the companion actually move along its predicted path around Betelgeuse over time, rather than simply appearing once in a single frozen image, still required a second observation, ideally from the opposite side of the orbit, roughly a year later. To be certain that the companion is really there, we still need to observe it in 1 year on the other side of the star, but there is very little space left for doubt, Montage said. Very little space left for doubt. Not none. Even at the moment of the clearest image ever taken of this object, one of the Discovery's own scientists was still holding open, deliberately, a sliver of room for the universe to surprise him again, and there was a third line of evidence, still developing entirely independently of both the Gemini detection and the VLT image. One that would not directly photograph the companion at all, but would instead prove its existence by the damage it was leaving behind, like a detective identifying a suspect not from a photograph but from the disturbed dust of a room they had just walked through. Every discovery in this story eventually leads back to one name, and it is worth slowing down here, because the science alone does not fully explain why this particular chapter of the Betelgeuse story matters as much as it does. Her name is Andrea Dupree, and by the time the companion's wake finally showed up in her data in the mid-2020s, she had already spent 40 years of her professional life pointed, in one form or another, at this single star. Dupree's relationship with Betelgeuse did not begin as a search for a hidden companion. It began in the mid-1980s as a much broader question about how giant, aging stars behave, what their surfaces actually look like, how they lose mass, how they change as they approach the ends of their lives. At the time she started, nobody had ever photographed the actual surface of any star other than our own Sun. Every other star in the night sky, no matter how large or how close, was optically unresolvable, a single point of light, its surface details forever hidden behind the fundamental limits of the telescopes available. Betelgeuse, despite being one of the largest stars visible from Earth, was no exception. It too was just a dot, however bright. That changed in 1995. Using the Hubble Space Telescope's faint object camera, Dupree and her collaborators captured what remains, to this day, one of the genuinely landmark images in observational astronomy. The first direct photograph of the surface of a star other than our own Sun. It showed Betelgeuse not as a featureless point, but as a mottled, textured disk. An ultraviolet image revealing a surface marked by enormous convective cells, hot spots, and structural irregularities utterly unlike the placid, uniform disk most people unconsciously picture when they imagine a star. I try, sometimes, to imagine what that moment must have felt like in the control room. The first time in the entire history of astronomy that a human being looked at a magnified image and saw the actual textured surface of a star that was not the Sun. Every stellar surface before that had been an abstraction, a mathematical inference derived from spectra and brightness curves. Dupree made one real. To my mind, that single image on its own would have justified an entire career. She kept going for 3 more decades after it. Across those decades, Dupree built one of the most comprehensive long-term observational records of any single star in the sky, watching Betelgeuse's brightness fluctuate, its surface features shift, its outer atmosphere billow and contract. She was among the lead scientists who, in the aftermath of the 2019-2020 Great Dimming, helped confirm that the star's dramatic fade had been caused by an ejected dust cloud rather than an approaching supernova, carefully, patiently untangling public panic from physical reality using data, not reassurance. Dupree, who has been studying Betelgeuse since 1985, hopes to continue studying the star in hopes of catching it, eject another gas bubble. Read one contemporary account of her work at the time, a description that captures something essential about the particular temperament this kind of research demands. Not the desire for a single dramatic breakthrough, but the patience to keep watching, year after year, for the next small anomaly that might finally explain the ones that came before. That patience paid off in a way Dupree herself likely could not have precisely predicted when she started. By the mid-2020s, with the companion's existence now supported by both the Gemini North detection and the VLT direct image, Dupree turned her attention to a different, harder question. Could the companion's presence be confirmed not by photographing it directly, but by finding the physical evidence of its passage through Betelgeuse's own outer atmosphere, the disturbance it should be leaving behind as it ploughed, orbit after orbit, through gas that Betelgeuse had exhaled across its own long, slow decline? The method Dupree's team eventually used required tracking subtle shifts in Betelgeuse's ultraviolet spectrum, the specific wavelengths of light emitted and absorbed by different chemical elements in the star's outer atmosphere, across nearly 8 full years of Hubble observations, supplemented by data from ground-based telescopes at the Fred Lawrence Whipple Observatory and the Roque de los Muchachos Observatory in the Canary Islands. 8 years. Roughly 2,900 days of patient, methodical observation layered on top of the 40 years Dupree had already spent watching this single star, all in pursuit of a signal so subtle it required nearly a decade of accumulated data before it could be statistically distinguished from noise. What she found, when the analysis finally resolved, was described in her own words with a simplicity that somehow made the discovery more vivid rather than less. It's a bit like a boat moving through water. The companion star creates a ripple effect in Betelgeuse's atmosphere that we can actually see in the data. The spectral data revealed a clear repeating pattern, a trail of denser gas, a literal wake expanding outward through Betelgeuse's extended atmosphere in a pattern that appeared consistently just after the companion crossed in front of the supergiant from Earth's point of view, once every roughly 2,100 days, precisely matching the century-old long secondary period that had confounded astronomers since before any of the current research team had been born. For the first time, we're seeing direct signs of this wake, or trail of gas, confirming that Betelgeuse really does have a hidden companion shaping its appearance and behaviour. Dupree said, when the results were presented at the American Astronomical Society's 247th meeting in Phoenix, Arizona, in January 2026, it is worth sitting for a moment with the shape of that sentence and with everything it represents. This was not a new detection of the companion itself. It was proof, arrived at through an entirely separate line of evidence, that the companion Gemini had photographed in 2024, and the VLT had imaged again more clearly still, was not merely present but actively, physically disturbing the enormous star it orbits, leaving fingerprints in the gas, evidence that could be traced, measured and dated across 8 years of accumulated observation. The idea that Betelgeuse had an undetected companion has been gaining in popularity for the past several years, but without direct evidence, it was an unproven theory, Dupree said. With this new direct evidence, Betelgeuse gives us a front-row seat to watch how a giant star changes over time. Finding the wake from its companion means we can now understand how stars like this evolve, shed material, and eventually explode as supernovae. There is a particular kind of scientific closure embedded in that statement, but it is not the closure of an ending, it is the closure of a threshold being crossed. 41 years after Dupree began studying this star, 31 years after she captured the first ever photograph of a stellar surface that was not our Sun's. Roughly a century after John Herschel first documented the star's mysterious slow flicker, and after decades of failed companion searches by other astronomers who never lived to see this vindication. All of it converges in January 2026 in a spectral wake pattern that finally, definitively, ties a name to a shadow that had been hiding in plain sight for longer than anyone currently working on the problem had been alive. That name, incidentally, is where the human story bends briefly towards something almost tender, because Betelgeuse's name, as we established earlier, derives from Yad al-Jawza, the hand of al-Jawza, referring to the mythological giant figure ancient Arab astronomers saw traced across that portion of the sky. When it came time to formally name the companion, teams working on the discovery, drawing on both the Gemini and CFA research groups, proposed Siwaha, an Arabic word meaning her bracelet. a bracelet worn on the hand, a small orbiting adornment sitting close against the giant's wrist, exactly where the mythology had always imagined a hand to be, exactly where the physics now confirms a companion actually orbits. Centuries of human storytelling and a century of rigorous scientific measurement arrived, independently and by pure linguistic coincidence, at the same poetic shape. Something small, wrapped closely around something enormous, catching the light. I do not think that naming choice was strictly necessary, scientifically speaking. Astronomers could have gone with a catalogue designation and moved on, and nobody outside the field would have blinked. But they didn't. They reached, instead, for something that honoured the shape of the mythology the star had always carried. And in doing so, they gave the discovery a kind of narrative completeness that pure data alone rarely provides. Siwaha, her bracelet, a small, hot, still-forming star, doomed to spiral inward and eventually be consumed by the giant it orbits, named for an ornament worn on a hand that people have been looking up at and telling stories about. For over 2,000 years, Dupree is still working. As of the most recent public statements associated with this research, astronomers are already planning the next major observing opportunity, timed for November 2027, when Siwaha will swing back out to its point of maximum apparent separation from Betelgeuse, the same geometric window that made the 2024 Gemini and VLT detections possible in the first place. It will be the first chance, since the wake detection was confirmed, for the object itself to be directly re-imaged, its orbital motion tracked, its mass more precisely pinned down, its future more confidently modelled. Dupree, by that point, will have spent 42 years studying this single star. She will very likely still be watching. It would be a mistake to treat this discovery as a piece of trivia about one unusual star tucked away in a corner of Orion, interesting only to the small community of astronomers who have devoted careers to studying it. The stakes here reach considerably further than that, and they reach in several directions at once. Into how we understand the deaths of massive stars generally, into how we count and classify the stellar population of our entire galaxy, and into a question that sounds almost philosophical until you realise it has a hard, measurable, physical answer. How many of the stars we have always assumed were solitary are in fact quietly hiding something we simply have not yet had the resolution to see? Start with the most immediate implication, the one closest to Betelgeuse itself. Models built around the newly confirmed companion suggest that Siwaha's fate is not a peaceful one, locked in an orbit that already carries it through Betelgeuse's own extended outer atmosphere, a region of space thick with gas the supergiant has been slowly, steadily exhaling across its own decline. Siwaha is subject to a relentless combination of atmospheric drag and extreme tidal forces. Every orbit, the companion loses a small amount of energy to friction against the gas it's dragging through, and every orbit, the immense gravitational pull of a star roughly 10 to 12 times its own mass stretches and strains it a little further. The models are consistent on the outcome, even if the exact timeline carries genuine uncertainty. Within roughly the next 10,000 years, an astronomical eye blink, Siwaha will spiral inward far enough to be consumed entirely by the star it orbits. 10,000 years sounds, at first pass, like an eternity on a human scale, longer than the entire span of recorded human civilization, stretching back before the pyramids, before written language, before agriculture reshaped how our species organised itself. And yet in stellar terms it is nothing. It is a heartbeat, a single held breath in the multi-million-year lifespan of a massive star. Somewhere in the relatively near astronomical future, a small, hot, still-forming star will be torn apart and absorbed by the enormous, unstable giant it has been quietly orbiting since the two of them were born together roughly 10 million years ago. That is not a hypothetical eventuality reserved for some distant epoch beyond meaningful comprehension. It is closer, in cosmic terms, to something that could plausibly be witnessed, in its opening stages at least, by a civilization not meaningfully more advanced than our own. What happens when a companion star spirals into a red supergiant is not merely an academic curiosity. It touches directly on one of the strangest theoretical objects in all of astrophysics, the Thorne-Zitkow object, a conjectured hybrid star first proposed in a 1975 paper by physicists Kip Thorne and Anna Zitkow, in which a compact, dense stellar remnant becomes embedded deep within the bloated outer envelope of a much larger star. The two effectively fused into a single chimeric object that superficially resembles an ordinary red supergiant from the outside, while harbouring something extraordinary at its core. For nearly 50 years, Thorne-Zitkow objects existed purely as theory, mathematically plausible, but with no confirmed real-world example, a kind of astrophysical unicorn that some researchers doubted would ever be directly identified. Some research teams have already speculated openly that Betelgeuse's future collision with Siwaha, whenever it finally occurs, could produce something resembling exactly this kind of exotic hybrid object. Not merely a supernova, but a merger event, unlike almost anything else catalogued in the modern astronomical record. Consider what that means for how we think about Betelgeuse's eventual death. For most of the 20th century, the assumption embedded in every model of Betelgeuse's future was simple. A massive aging star exhausts its fuel, its core collapses, and it detonates as a Type II supernova, following a well-understood, thoroughly modelled sequence that astronomers have documented in dozens of similar stars across the galaxy. Add a companion, one that is actively spiralling inward, actively due to merge with the star before that supernova is expected to occur, and the entire predictive model becomes something considerably more uncertain and considerably more compelling. Will Siwaha's infall trigger instabilities that accelerate Betelgeuse's collapse? Will the merger itself produce visible eruptions, flares, or brightness changes decades or centuries before any final explosion? Will the supernova, when it finally arrives, look meaningfully different from a standard Type II event because of what happened to the star that fed into it? Nobody currently knows. That uncertainty is not a gap in the science waiting to be politely filled in. It is a live, open question that this single discovery has forced back onto the table for an entire subfield of astrophysics. And when Betelgeuse does finally explode, whether that happens in 10,000 years, 100,000 years, or, by the most optimistic and most contested estimates published in recent years, conceivably within mere decades, the event will not be a quiet academic footnote. At a distance of roughly 650 light-years, well beyond any range at which a supernova could pose direct physical danger to Earth, Betelgeuse's death will nonetheless be one of the most visually spectacular astronomical events witnessed by human civilization in recorded history. Astronomers estimate the explosion could reach an apparent magnitude somewhere between -8 and -12, bright enough to be clearly, unmistakably visible in broad daylight for months, potentially up to a year, and bright enough at night to cast faint shadows on the ground, a genuinely new light source hanging in Earth's sky, rivaling or briefly exceeding the brightness of the full moon, depending on precisely how the explosion unfolds. Before any of that visible light even arrives, the collapse of Betelgeuse's core would release an almost incomprehensible burst of neutrinos. A supernova at 650 light-years would deliver, by some estimates, roughly 64 zeros and times the number of neutrinos detected on Earth from supernova 1987A, the last supernova visible to the naked eye, which itself occurred roughly 168,000 light-years away in a neighbouring galaxy. Every neutrino detector on the planet, most of them built and buried specifically to watch for exactly this kind of event, would register a flood of signal unlike anything in the modern instrumental record, arriving hours before the visible light itself, racing ahead through matter that starlight cannot pass through unimpeded. This is, to my mind, one of the more genuinely consequential discoveries connected to Betelgeuse in decades. Not because Siwaha's existence changes the timeline of that eventual supernova in any confirmed way, but because it fundamentally alters what kind of star we now understand is standing at the edge of that explosion. We are not simply watching a single isolated massive star approach the end of its life on a well-understood, textbook trajectory. We are watching a binary system, one member of which is actively slowly being consumed by the other in real time, with measurable orbital decay on a timescale short enough that the process itself is scientifically observable rather than purely theoretical. Every model of Betelgeuse's future, every prediction of when, how, and in what form it will finally detonate, now has to account for a variable that, until 2024, was not even confirmed to exist. The implications reach well beyond this single star too, and this is where the stakes climb from one famous star just got more complicated to something closer to a genuine reconsideration of how common this kind of hidden binarity might actually be throughout the galaxy. Betelgeuse's is, by a considerable margin, the closest and most thoroughly studied red supergiant to Earth, the one star of its kind that we have the observational history, the archival data, and the sheer accumulated human attention to actually catch a hidden companion around, given more than a century of trying. If a companion this close, this deeply embedded, this thoroughly camouflaged by its host star's overwhelming glare, existed around the best-studied red supergiant in the sky, and still took over 100 years to confirm, what does that suggest about every other red supergiant we have never studied nearly as closely? Antares, Rigel, the thousands of aging, massive stars scattered across our galaxy and its neighbours, each one a candidate for exactly the same kind of hidden binary system, each one currently modelled, in most astrophysical calculations, as if it were solitary, simply because nobody has yet had the reason, the funding, or the century of accumulated data required to prove otherwise. That question, how many of the massive, dying stars we currently model as single are in fact quietly binary, is not a small one. It touches directly on how astronomers calculate the rate at which supernovae should occur across the galaxy, how neutron stars and black holes form and pair off with each other, and how accurately we can predict the gravitational wave signatures produced when compact stellar remnants eventually merge, a phenomenon now routinely detected by observatories like LIGO and Virgo here on Earth. Every one of those calculations rests ultimately on assumptions about how common binary companionship is among massive stars as they approach the ends of their lives. If Betelgeuse, the single most observed, most photographed, most historically documented massive star in Earth's entire sky, was quietly hiding a companion for over a century of dedicated searching, the honest, uncomfortable statistical question becomes whether solitary massive stars are the exception astronomers have long assumed them to be, or whether they are, in fact, the rare cases, and companionship of exactly this hidden, camouflaged kind is closer to the default. I find something genuinely unsettling in the best possible sense about how quickly the scale of this question grows once you actually follow it outward from a single star. We began this chapter with Betelgeuse and Siwaha, one giant, one small companion, one orbit, one impending merger roughly 10,000 years from now. We end it with a question mark hanging over the statistical architecture of massive star death across the entire visible universe. That is not a small escalation for a single detection built on a signal-to-noise ratio that, by one team's own honest admission, barely cleared the threshold most astronomers use to distinguish real evidence from noise. But that is precisely how the largest reconsiderations in science tend to begin, not with a grand, unambiguous announcement, but with one particularly stubborn, particularly well-documented anomaly that simply refuses to resolve cleanly, until enough careful people, across enough independent teams, using enough different instruments, finally converge on the same uncomfortable, exhilarating answer. We were wrong about what alone actually looks like. Every discovery this significant deserves to be tested against its own weakest points before it earns the right to be believed. And Betelgeuse's companion has, if anything, been tested more rigorously than most stellar discoveries manage in their first few years of existence, largely because 3 separate research teams arrived at overlapping but not identical conclusions using 3 fundamentally different observational techniques, and none of them were willing to simply defer to the other's numbers without scrutiny. That friction, uncomfortable as it can look from the outside, is precisely how legitimate scientific consensus gets built. It is worth walking through the actual texture of that friction here, because the credibility of this entire story depends on understanding not just what was found, but exactly how hard it was to confirm, and exactly how much still remains genuinely, honestly uncertain. Begin with the most basic disagreement: mass. Steve Howell's Gemini North team, working from speckle imaging data captured in December 2024, estimated the companion's mass at roughly 1.5 times that of the Sun, characterizing it as an A or B-type pre-main sequence star. Miguel Montage's team, working from VLT sphere data captured during that same observational window but processed and analysed independently, arrived at a heavier estimate, somewhere between 2 and 3 solar masses. These are not trivial rounding differences. A companion at 1.5 solar masses and a companion at nearly 3 solar masses represent meaningfully different physical objects, with different internal structures, different eventual evolutionary paths, and different implications for exactly how violently the eventual merger with Betelgeuse will unfold. Montage himself offered a candid explanation for the discrepancy that doubles as an admission of how close this entire discovery came to not happening at all. Because it is more massive than predicted, we see it, he said, suggesting that the companion may simply be more massive, and thus intrinsically brighter, than the original theoretical models anticipated, which is precisely why the VLT was able to capture such a comparatively clean, high-confidence image, while Gemini's earlier detection sat right at the ragged edge of statistical significance. If the companion had turned out to be exactly as faint as the original 2023 and 2024 predictions suggested, it is entirely possible that neither Hubble, nor Chandra, nor even Gemini's speckle imaging, nor the VLT's sphere instrument would have been able to see it at all. We may have gotten fortunate, in other words, in exactly the specific way that made this discovery possible within our current technological reach. A sobering thought, given how many other, fainter companions around other stars might still be sitting entirely beyond what any instrument currently operating can resolve. Then there is the deeper, more fundamental question of confirmation itself. And this is where responsible science insists on being uncomfortable rather than triumphant. The Gemini North detection, by the team's own published assessment, carried a signal-to-noise ratio of roughly 1.6, a number that, translated out of statistical jargon, means the detected signal was barely more than 1.5 times stronger than the random background noise inherent to the instrument and the observing conditions that night. René Udmajer's blunt assessment bears repeating here in full, because it represents exactly the kind of skepticism good science requires and rarely receives enough public credit for providing. Such values are widely regarded as non-detections. That is not a minor caveat tucked into a footnote. That is a senior astronomer, entirely uninvolved in the discovery, publicly stating that by the field's own conventional standards, the initial Gemini result should probably not have been described as a confirmed detection at all. Howell's team, to their credit, never claimed otherwise with false confidence. Their own published estimate placed roughly a 10% probability that the object they photographed was not a real companion, but an artifact of noise, atmospheric distortion, or some other confounding factor entirely unrelated to Betelgeuse's actual orbital environment. 90% confidence sounds, on the surface, reasonably solid, comfortably better than a coin flip, certainly compelling enough to justify further investigation. But 90% confidence, applied to a discovery this consequential, still leaves a 1 in 10 chance that an entire subsequent wave of research, funding, telescope time, and public attention was chasing something that was never actually there. That is the genuine, uncomfortable state the Betelgeuse companion hypothesis occupied for the better part of a year after the initial Gemini announcement. Tantalizing, plausible, aligned with over a century of theoretical prediction, and still, by rigorous statistical standards, unconfirmed. What changed that calculus was not a single knockout observation, but the accumulation of independent, differently flawed evidence converging on the same conclusion from angles that shared no common source of potential error. This is, in fact, exactly how the most durable scientific consensus tends to form, and it is worth naming explicitly, because it is easy to mistake for weakness what is actually one of science's greatest structural strengths. Montargis' VLT image did not simply repeat Howell's Gemini detection using the same method, the same instrument, or the same potential sources of systematic error. It used an entirely different telescope, an entirely different imaging technique originally designed for exoplanet detection, an entirely different data processing pipeline, and an entirely independent research team with no stake in defending Howell's specific numbers. If the Gemini detection had been a statistical fluke, noise dressed up to look like a companion, there would have been no principled reason for an unrelated European team, using unrelated hardware, to stumble onto an object in almost exactly the same predicted location during the same predicted observing window. The fact that they did is precisely the kind of independent corroboration that transforms a shaky 90% detection into something considerably closer to settled fact. Montargis' own caution remains instructive here, though, even with what he called the clearest image ever of the object, he stopped short of full certainty, noting that confirming true orbital motion still required a follow-up observation from the opposite side of Betelgeuse roughly a year later. "There is very little space left for doubt," he said. Not there is no doubt left. That distinction matters, and a careful storyteller should resist smoothing it away for the sake of a cleaner narrative. The third line of evidence, and in many ways the most methodologically distinct of the three, came from Andrea Dupree's team and their nearly 8-year analysis of Hubble ultraviolet spectroscopy, published and presented at the American Astronomical Society's 247th meeting in January 2026. This evidence did not attempt to photograph the companion at all. It sidestepped the entire brightness contrast problem that had made direct imaging so difficult in the first place, and instead searched for the companion's gravitational and physical influence on the gas surrounding it. The logic here is worth spelling out clearly because it represents a fundamentally different kind of proof than a photograph. If a companion star is truly orbiting through Betelgeuse's extended atmosphere, it should be dragging a wake of disturbed, denser gas behind it, the way a boat's hull disturbs the water it moves through, and that wake should leave a measurable, repeating signature in the spectral lines of iron and other elements present in that gas, appearing at a predictable phase in the companion's roughly 2,100-day orbital cycle. Dupree's team found exactly that signature, appearing exactly when the orbital models predicted it should, across nearly 8 years of accumulated data spanning from 2019 to the mid-2020s. For the first time, we're seeing direct signs of this wake, or trail of gas, confirming that Betelgeuse really does have a hidden companion shaping its appearance and behaviour. Dupree said, "What makes this third line of evidence so valuable, from a purely epistemological standpoint, is precisely that it does not depend on resolving the same brightness contrast problem that plagued both the Gemini and VLT detections. It is not vulnerable to the same category of instrumental noise, the same atmospheric seeing conditions, or the same processing artifacts that could, in principle, have produced a false positive point source in either of the direct imaging attempts. 3 teams, 3 instruments, 3 completely different physical signatures, a faint point of light in speckle imaging data, a brighter point of light in adaptive optics imaging data, and a repeating spectral disturbance pattern in ultraviolet spectroscopy data spanning nearly a decade. 3 independent paths converging on the same conclusion is a considerably stronger form of evidence than any single path travelled alone, however imperfect each individual path remains when examined in isolation. And yet, and this matters, because a responsible account of this discovery should never pretend the story has fully closed. Genuine, substantive uncertainty remains layered throughout nearly every specific claim associated with this companion. the exact mass still carries a real range from roughly 1.5 to nearly 3 solar masses, depending on which team's analysis you weight most heavily, and that range has direct consequences for how astronomers model the eventual merger and its effect on Betelgeuse's supernova timeline. The precise nature of the companion, whether it is genuinely a pre-main sequence A or B type star, as Howell's team characterized it, or something closer to the heavier, more evolved characterization implied by Montargis' revised mass estimate, remains an open question that will require additional spectroscopic study to resolve definitively. Even the relationship between the individual pieces of evidence deserves careful scrutiny. It remains formally possible, though increasingly statistically improbable given the convergent evidence, Dupree's wake detection and the direct imaging detections from Gemini and the VLT are documenting subtly different aspects of a more complicated system than currently modelled, perhaps even hinting, as some researchers have speculated more provocatively, at additional structure or even multiple bodies contributing to Betelgeuse's long secondary period, rather than a single clean companion accounting for the entire signal. There is also the awkward, rarely discussed matter of how the earlier failed searches fit into this picture. Both Hubble's direct imaging attempts and Chandra's X-ray searches, conducted before the 2024 predictions narrowed down the exact orbital geometry and timing, came back with nothing usable, and it would be intellectually dishonest to simply wave that away as a matter of those earlier attempts being pointed at the wrong moment in the orbit. It remains genuinely unclear, even now, precisely why those searches failed so completely, while the more targeted, precisely timed 2024 attempts succeeded, at least partially. Was it purely a matter of orbital geometry, catching the companion at its point of maximum apparent separation, rather than at some less favourable phase of its 2,100-day cycle? Or did the specific instrumentation used in the 2024 detections, speckle imaging's ability to defeat atmospheric blurring, spares purpose-built exoplanet hunting optics, matter as much as the timing itself? The honest answer at the time of this writing is that nobody has published a fully satisfying account that separates those two variables with confidence. That gap in the story is not a minor loose thread. It is a genuine, open methodological question that the 2027 follow-up observations, already being planned by multiple teams, are specifically designed to help resolve. I find, if I am honest, that this layered, imperfect, still negotiating with its self-quality is precisely what makes this discovery more trustworthy to me than a cleaner narrative would have. Real science does not usually announce itself with a single unambiguous photograph and a unanimous chorus of agreement. It arrives, far more often, exactly the way this story arrived, as a series of partial, individually contestable pieces of evidence, gathered by competing teams with genuinely different methods and genuinely different professional incentives, none of whom were willing to simply take the other's word for it, all of whom kept pushing, kept rechecking, kept publishing honest caveats about signal-to-noise ratios and remaining uncertainty, even as the overall weight of evidence tilted increasingly toward confirmation. That is not a flaw in how this discovery unfolded. That is, to my mind, the discovery working exactly as it should, messy, contested, self-correcting, and ultimately more convincing precisely because nobody involved pretended it was simple. What we can say, with genuine confidence as of the most recent published research, is this: Betelgeuse almost certainly has a companion star. That companion is very likely a young, hot, still-forming object with a mass somewhere between roughly 1.5 and 3 times that of our Sun. It orbits on a period of roughly 100 days, physically passing through Betelgeuse's own extended outer atmosphere as it does, and it leaves a measurable wake of disturbed gas behind it that has now been independently confirmed across nearly 8 years of ultraviolet spectroscopic data. It is very likely doomed, on a timescale of roughly 10,000 years, to spiral inward and be consumed by the star it orbits, in a merger event whose exact consequences for Betelgeuse's eventual supernova remain genuinely, actively unknown. Everything beyond that, the precise mass, the precise nature of the object, the precise mechanism by which its eventual demise will interact with Betelgeuse's own death, remains an open, contested, actively researched question, one that will not be fully resolved until the next observing window opens in November 2027, and very likely not fully resolved even then. That is not, I want to be clear, a disappointing place for this story to sit. A century of astronomers asked whether Betelgeuse was truly alone. 3 independent teams, using 3 independent methods, have now converged on the same answer. No, it never was. The remaining uncertainty is not evidence that the discovery is weak. It is evidence that the discovery is real enough and significant enough that the scientific community is now doing the hard, unglamorous, essential work of getting every remaining detail exactly right. Because a discovery this consequential deserves nothing less than that level of scrutiny before it gets written permanently into the textbooks that will teach the next generation of astronomers how massive stars actually live and how they actually die. The next chapter of this story already has a date attached to it, and that date is close enough to feel less like distant speculation and more like an appointment already circled on multiple observatory calendars. November 2027. That is when Siwaha, following its roughly 2,100-day orbital clock, will swing back out to its point of maximum apparent separation from Betelgeuse as seen from Earth. The same geometric alignment that made the December 2024 detections possible in the first place, and the first genuine opportunity since then to observe the companion under comparably favourable conditions. What astronomers are hoping to accomplish in that window reads almost like a checklist of everything the current evidence has left unresolved. Foremost among the goals is the direct confirmation of orbital motion. Actually watching Siwaha occupy a measurably different position relative to Betelgeuse than it did in the 2024 images, moving along a path consistent with genuine gravitational binding rather than sitting still as a coincidental background object or a persistent processing artifact. Montages himself flagged this explicitly as the outstanding requirement for full certainty, and multiple teams, including his own at the Observatoire de Paris and Howell's at NASA Ames, are already preparing follow-up proposals for both the VLT's spare instrument and Gemini North's speckle imaging capability, hoping to repeat and refine their respective 2024 techniques with the benefit of 2 additional years of instrumental calibration and, in some cases, upgraded hardware. There is also a genuine possibility that entirely new instruments not available during the 2024 window will join the effort by 2027. The extremely large telescope currently under construction by the European Southern Observatory at Cerro Armazones in Chile is designed around a primary mirror roughly 39 meters in diameter, an aperture so large it will dwarf every optical telescope currently in operation, offering a theoretical resolving power that could, if the telescope reaches early operational readiness in time, resolve details of the Betelgeuse-Siwaha system that remain entirely beyond the reach of Gemini's 8.1 meter mirror or the VLT's individual 8.2 meter units. Whether the ELT achieves first light in time to contribute meaningfully to the 2027 observing campaign remains uncertain, tied as it is to the ordinary uncertainties of large infrastructure construction timelines. But the mere possibility illustrates something important about where this field is heading. The technology required to resolve companions this faint, this deeply embedded in their host star's glare, has only existed at all for the past few years, and it is improving rapidly enough that questions considered unanswerable a decade ago are now cautiously being scheduled. Beyond simply reconfirming what has already been found, the 2027 observing window and its successors carry the potential to resolve the deeper, more consequential uncertainties this discovery has opened. Astronomers hope to narrow the still disputed mass estimate, currently ranging from roughly 1.5 to nearly 3 solar masses, depending on which team's analysis is weighted most heavily, using additional spectroscopic data that could more precisely characterize Siwaha's temperature, luminosity, and evolutionary stage. A tighter mass constraint would in turn sharpen every downstream prediction about the eventual merger between Siwaha and Betelgeuse, how violently it will unfold, what visible signatures it might produce decades or centuries in advance, and whether it will meaningfully alter the timeline or character of Betelgeuse's eventual supernova. That last question deserves particular attention because it sits at the intersection of pure scientific curiosity and something considerably closer to practical civilization-scale relevance. Betelgeuse remains, by most current estimates, one of the nearest confirmed supernova candidates to Earth, and while the 650 light-year distance places it safely beyond any range at which the explosion itself could pose direct physical danger, the event would nonetheless represent one of the most significant naked-eye astronomical spectacles in recorded human history. Visible in daylight for months, dramatically reshaping the night sky for years afterward and delivering a neutrino signal that every major particle physics detector on the planet has been specifically calibrated, in part, to catch. Facilities like the Deep Underground Neutrino Experiment, still under construction in the United States, and existing detectors like Super Kamiokande in Japan and IceCube at the South Pole, are all, to varying degrees, standing ready for exactly this kind of event, and a supernova at Betelgeuse's distance would deliver a neutrino flux so far above background levels that every one of these instruments would register the event within minutes of the core collapse itself, hours before any visible light change became apparent to observers on Earth, confirming precisely how Siwaha's ongoing infall interacts with Betelgeuse's internal structure in the centuries or millennia leading up to that eventual collapse is not merely an academic curiosity. It is directly relevant to how confidently astronomers, and by extension the broader scientific infrastructure built to detect and respond to a nearby supernova, can predict when and how that event will actually unfold. The implications extend outward from Betelgeuse, specifically into a much broader observational campaign that this discovery has already begun to justify. If a companion this close, this deeply embedded, and this thoroughly camouflaged could hide around the single most studied red supergiant in Earth's sky for over a century before finally being confirmed, the logical next step, one several research groups have already begun pursuing, is to apply the same combination of long baseline archival analysis, targeted speckle imaging, and high-contrast adaptive optics to other nearby red supergiants and evolved massive stars. Antares, the bright red supergiant marking the heart of Scorpius, sits at a comparable distance to Betelgeuse and has its own history of unexplained brightness variability that has never been fully resolved. Other, less famous red supergiants scattered throughout the Milky Way and its satellite galaxies represent an entire population of stars that current models still largely treat as solitary, simply for lack of the century-plus observational archive and dedicated search effort that made Betelgeuse's companion detectable in the first place. Each one of those stars is now, at least implicitly, a candidate for the same kind of hidden companion, and the search techniques refined through the Betelgeuse effort, the statistical modelling of long secondary periods, the speckle imaging methods pioneered by Howell's team, the exoplanet hunting optics repurposed by Montages's team, the ultraviolet wake detection method developed by Dupree's team, now exist as a validated, transferable toolkit ready to be pointed at the next candidate. There is a broader statistical reckoning implied here too, one that touches directly on how astronomers model the population of massive stars across the entire galaxy, and by extension, how confidently we can predict phenomena that depend on that population, including the rate at which supernovae should occur, the rate at which neutron stars and black holes form, and eventually pair off with each other, and the rate at which those compact remnants merge and produce the gravitational wave signals now routinely detected by observatories like LIGO and Virgo. Every one of those predictions currently rests on assumptions about how common binary companionship is among massive, evolved stars. Assumptions that, until 2024, treated stars like Betelgeuse as effectively solitary simply because no companion had ever been confirmed. If a meaningful fraction of the galaxy's red supergiants turn out to harbour similarly hidden, similarly camouflaged companions, entire statistical models built on the assumption of stellar solitude may need meaningful revision, with consequences that ripple outward into fields as far removed from stellar astrophysics as gravitational wave astronomy, and the predicted frequency of compact object mergers detectable from Earth. And then there is the more distant, more speculative horizon, the eventual merger itself, and what it might teach us about an entirely theoretical class of object that has existed for 50 years only on paper. If Siwaha's slow inward spiral does eventually produce something resembling a Thorne-Zitkow object, even a short-lived transitional version of one, before Betelgeuse's own core collapse renders the question moot, it would represent the first direct confirmed real-world example of a hybrid stellar structure that theoretical astrophysicists have debated, modelled, and searched for without success since Kip Thorne and Anna Zitkow first proposed the concept in 1975. Locating and characterising such an object, even in its earliest, most ambiguous stages, would offer astronomers an unprecedented opportunity to test predictions about extreme stellar interiors that have until now existed purely as mathematical exercises, entirely untethered from direct observational confirmation. None of this, not the 2027 observing window, not the expanded search for hidden companions around other red supergiants, not the statistical reconsideration of massive star binarity, not the distant theoretical promise of a confirmed Thorne-Zitkow object, represents a finished story. Every single one of these threads is, as of this writing, an open, actively pursued research question, with specific dated milestones already scheduled and specific teams already competing and collaborating to answer them. That is, perhaps, the most honest way to characterise where this discovery currently stands. Not as a closed case, filed neatly away in a textbook chapter, but as a live, ongoing investigation with a confirmed starting point, a genuinely uncertain set of intermediate findings, and a horizon of future observations already scheduled to push the story further than anyone currently working on it has yet been able to see. There is something worth sitting with, quietly, before we let this story go. Not a conclusion, because this story does not have one yet, but an observation about the particular shape of what we have just spent this much time examining together. For well over a century, human beings looked up at Betelgeuse, tracked its slow, strange breathing, argued about what caused it, built and discarded theory after theory, and never once, in all that careful watching, correctly identified the thing that was actually there. We assumed solitude because solitude was simpler. We modelled the star as if it lived alone, because the alternative required a precision of instrument and a patience of observation that for most of that century simply did not exist yet, and the entire time, something small and hot and still forming was orbiting inside the giant's own exhaled breath, close enough to leave a wake in its atmosphere, far enough from our instruments to remain functionally invisible for generation after generation of astronomers who never got to learn what we now know. I keep returning, in thinking about this story, to how ordinary that particular kind of blindness actually is. Not a failure of intelligence or effort, but a simple, structural limitation of looking at something enormous and bright and assuming, because you cannot see anything else, that there is nothing else to see. It is, if I am honest, not so different from the way human beings sometimes misread each other. We look at someone we have known for years, someone bright enough and complicated enough to dominate our attention entirely, and we assume we have seen the whole of them, simply because the parts we can see are already so much to take in. Closeness is not the same thing as visibility. Proximity does not guarantee understanding. Betelgeuse has been the brightest, closest, most thoroughly observed red supergiant in Earth's entire sky, And it still took a century of dedicated searching, 3 independent research teams, and technology built specifically to defeat the very brightness that made the star famous in the first place, before anyone could confirm what had been sitting right beside it all along. That, to me, is the real weight of this discovery, not the specific mass of Siwaha, not the exact date of its eventual consumption, not even the tantalizing unresolved possibility of a confirmed Thorn-Zitkau object somewhere on the far side of 10,000 years. It is the reminder, delivered by one of the most famous and most watched stars in human history, that alone is a conclusion we reach far too easily and far too often, simply because we have run out of ways to look harder. How many other stars right now, tonight, visible from your own backyard if the sky happens to be clear, are quietly hosting something we have not yet had the patience, the technology, or the reason to search for closely enough to find? Nobody currently knows the answer to that question. I am not certain anyone alive today will know it in full, and I find that I do not need them to, in order to feel the full weight of what it means that we asked, somewhere, roughly 10,000 years from now, a span of time that feels enormous measured against a single human life, and feels like almost nothing measured against the age of the star itself. Siwaha will finally lose its long, slow battle against Betelgeuse's gravity and its own atmosphere's drag, and it will spiral inward for the last time, consumed by the very giant it has spent its entire brief existence orbiting. We will not be there to see it, not in any form recognizable to us now, but the star will still be there, and whatever intelligence exists to watch it, if any does, will inherit a night sky that has been quietly rearranging itself this whole time, on a clock too slow for any single generation to witness directly, but not too slow to eventually matter. Science does not always give us endings. Sometimes it gives us horizons, a next observing window in 2027, a next mass estimate still being refined, a next telescope with a mirror large enough to finally settle a question that a smaller one could only gesture toward. And perhaps that is precisely the point of this particular story. Not to arrive at a final, tidy answer about what Siwaha truly is, or exactly when Betelgeuse will finally die, but to keep the question alive, carefully, rigorously, honestly, long enough for someone younger and better equipped than any of us currently are to carry it the rest of the way. Andrea Dupree has already given 40 years of her working life to this single star, and she is, by every indication, not finished yet. Someone will eventually take her place at that particular instrument, pointed at that particular patch of sky, continuing a watch that began before any of us were born and will very likely continue after all of us are gone. We are the generation that finally confirmed Betelgeuse was never alone. The answer to everything that discovery still leaves open. What Siwaha truly is, how the merger will unfold, what the supernova will finally look like, and how many other stars across this galaxy are hiding exactly the same kind of quiet, camouflaged companionship, belongs